Hello everyone, welcome to this video on understanding ComfyUI nodes. In today's video, I will talk about the basic built-in nodes from ComfyUI, and I will explain how they work. Also talk a little bit about the technical side of a few of the nodes. Now, since there are a lot of custom nodes, I will not be able to cover all the custom nodes. Instead, I'm just going to focus on the built-ins. If you have a specific custom node you want me to cover in the future video, let me know in the comments down below. Let's get started with the most common node in my opinion, and that is the checkpoint loader symbol. You can find it by right-clicking, click on Add Node, go into Loaders, and then select Load Checkpoint. Alternatively, you can double-click and search for checkpoint, and then select the Load Checkpoint loader symbol. Now this node is quite straightforward to understand. It has a single input, and that is in the form of a checkpoint name. These checkpoints can be found under the ComfyUI folder, and then go into models and then checkpoints. You will see the checkpoints there. If you do not have any, you will paste your checkpoint in this folder. Now the main purpose of this particular node is to load the checkpoint or the models without any additional configuration. Now, if you search for load checkpoint in this search, you will see that before we had a node called checkpoint loader, and right now it's saying deprecated. That because we no longer need it. The simple version basically is replacing the other one. And previously we had to find the model plus a configuration file, but with this simple checkpoint, it's no longer required. It will automatically get the correct configuration. Now, this checkpoint name is basically a string. In code, it's str. So this means that we can right-click on the node and select Convert Checkpoint Name to Input. This will give us an input field. We can take this input field, drag out, select Add Node, Utils, and primitive. And now we have a primitive node which can be used to control the value of the checkpoint name in the load checkpoint. So for example, we can change the control of the generate to randomize, and then each time we click on QProp, it's going to randomize the checkpoint that we'll use. However, this process will require loading and unloading the checkpoint multiple times. So if you're experimenting, you can use this method. I would suggest to go with incremental, select your first checkpoint, and then each time it will just go and change the checkpoint. So go into the second, third, fourth, and so on, how many checkpoints you have. Okay, now this checkpoint is one of the few checkpoints which takes one input, but it has 3 different outputs. The first one is model, and most of the time it will go into a KSampler. The second one is clip, and this one goes into a clip text encode. And then the last one is VAE. In a simple text to image workflow, this VAE will go into a VAE decode node, which is usually after the KSampler. So the order will be the first thing from clip, it goes into a clip text encode. This can be a positive or negative. The model will go into the KSampler, and then the VAE will be the last thing in the pipeline inside the VAE decode. So let's start with the clip. The main purpose of the clip is to first take the positive input and the negative. They both work the same way, and then it will do something that's called as tokenization. So it will convert them into individual tokens. Once we have those tokens, it will then change it into a bunch of numbers. These numbers basically is what the conditioning is. So that's the process of the clip. For example, let's say you type in a woman. This will get converted to one girl. It's going to depend on the checkpoint that you have, but most of the time you will see this, especially if you're using something like an anime like model. And then if you have one girl, that also get converted into the number 1 girl. Lady, that also will get converted into one girl. So this is the token form. And because this is still in text format, and when it comes to machine learning, computers generally, they prefer numbers. So this text gets converted into numbers, and the output is basically like a conditioning. That conditioning will go to the KSampler. Okay, so that's basically the clip. And this whole process, basically this entire thing here, it happens inside the clip text encode. Now let's take a step back. Let's go back into the model, and the model is just a UNet. So if you're training your own model, you may have a UNet format, and you can actually load a UNet individually by double clicking and searching for UNet. You will have a UNet loader. Now similarly, the clip can also be loaded by itself. There is a load clip here. The VAE also has one where you can load the VAE individually. So basically this load checkpoint is doing the job of the UNet loader, the load clip, as well as load VA, all in one. When you go online to download a particular checkpoint, you're most likely downloading this safetensors or maybe a .ckpt, and you can think of the safetensors or .ckpt file as a container. So you basically get a container like this, and inside it there will be the UNet, there's the clip, and then there is the VA. The load checkpoint main purpose is to separate these three and then give you so that you can pass it to the pipeline. Now we've already talked about the clip text encode. We've also looked at the model. Let's take a look at the VA. Before that, we may have to talk about latent diffusion model. Let's say we have a picture, and this is in the pixel space, or we still have pixel. The pixel value normally is represented as 255, 255, and let's just say 0 here. So this is going to be like RGB, like so. And what we see, we see an image representation, but when we pass that over to a computer, it will just get these numbers, right? If we are training a model using this format, we give it a bunch of numbers and we expect it to output the same thing. What could happen is that this is the picture that we are expecting to get, but the model is generating this image here. And at first glance, it may look exactly the same. So this is our expected result, and this is what is being generated by the model. And right now we are talking about the pixel space. When we get a result like that, we usually calculate a loss, and then based on the loss, we are going to tell the model to improve. But when we have these small changes, and right now, for those of you who did not see the change, basically like the eye is at this position, and this eye is slightly below. So for us, that's obviously not correct. But for a model, the loss would be quite low. Let's say it's 0.2. This is not enough to push the model to go towards a good direction, to improve. So what the Stable Diffusion team did was to go from a picture in pixel space, pass that over to get a latent space. And this conversion here is done by the VAE encode node in ComfyUI. And the way to think of it like that is, at first we have 255, 255, and 0 in this case. It will just convert it into numbers like this. This is not an exact representation. Now note that I am using this as a representation. The exact transformation from pixel value to latent space representation will depend on the specific architecture and training of the model. It is not a simple linear mapping. The latent space representation typically encodes features or characteristic of the input image in a lower dimensional space. And the purpose of this latent space is to capture essential information about the input image in a more compact and structured form that facilitate image generation. And for us, these numbers do not make a lot of sense, but for the computer, it's actually better, because now if we go from a latent space and we try to generate the same image, this loss will increase. And now we can tell the model to improve, so go towards a particular direction. Now, of course, if we go from a pixel space to latent space, we'll need some way to go from a latent space back to a pixel space. And this is done by the VAE decode node inside of ComfyUI. All right, so now we know about the model, the clip, variational autoencoder. Now in a text to image workflow, we are generating the latent space image by using an empty latent image. So this node will give us a latent space image, but in an image to image workflow, we are going to have load image. And because this load image is just loading an image, so we are still in the pixel space, we use the VAE encode node to convert that into the latent space. And that is where we can drag the VAE into this VAE encode so that it does the conversion. Now, one thing to note here is that when we go from a pixel space to the latent space, we are losing a little bit of information. So it's important to know that if you have a complex workflow where you're going from image to latent, and then you're decoding that image back to the pixel space, if you take that output image and then pass it over to, let's say, an upscaler, and then you go back into another KSampler for a second pass, each time you are doing the encoding and decoding, you're losing a little bit of information. All right. So now I have the clip text encode, which is green. That's going to be the positive, and the negative one is going to be red. I'm going to change it to some safeguard for YouTube. All right. Now, next, let's go into the most complex one, I think, which is the KSampler. Because this one, as you can see, it's taking a lot of inputs and just outputting one. This is the most common node type that you will see, where you have multiple inputs into a node, and then we just get one single output. Now for this KSampler, it requires the model, which comes from the load checkpoint, and then it requires a positive, negative, which is basically the conditioning from the clip text encode. We're going to take the positive clip text encode into the positive node, and then negative into negative. For the latent image, we can grab from the empty latent image, or we can pass an image, convert it into latent space, and then pass it over to the KSampler. Now, the KSampler is designed to do the sampling steps, basically the sampling operation. So for now, think of it like we have an image, and this is just noise, like a bunch of noise. We don't have anything. What the KSampler will do is at each step is going to denoise it slightly so that we start getting a pattern or an image. So at this point, maybe we get the head here, and then we start getting the hair, and finally we have the actual image, right? So this process of going from a noisy image to a clear image, that's the responsibility of the KSampler. By the way, if you're looking to see the code, how exactly this is happening, KSampler class, you just have a function called sample, and then inside it, it's using another function called common KSampler. And if you want to see the code, you will need to look for the function common KSampler and see how that works. So these are all the inputs that it requires, and then it's just outputting a latent. So back to ComfyUI, the latent will go into a VAE decoder, and we've already talked about this VAE decode, what exactly it's doing. It requires the samples is just latent, and then VAE will get it from the model. You can use the load VAE node to load a specific VAE if you have one. And this one is just going to convert from latent back into an image, which we can view it by using a save node or a preview image node. Now, let's talk about the seed. Think of the seed number as the starting point for generating pseudo-random numbers. Basically, if all other variables are the same and you use the same seed, you will get the same result each time. So the seed ensures reproducibility, and it helps to get consistent results. Now, in ComfyUI, the seed has a minimum value of 0 and a maximum value of this hexadecimal number. In Python, if we were to convert it from hexadecimal number to integer, we are going to get this big number. For the most part, you should not be running out of seed number when generating image. Basically, think of it like this. You have this big number here. You are going to multiply this by the number of steps. Then you can multiply this by the number of K-samplers you have. Multiply the result by the number of noise scheduler. Multiply that by the positive prop. Basically, how many numbers or tokens we have in that model. Multiply that by the negative prop. You're going to get a lot of images that you can generate from it. Now next, let's talk about the step or inference step. In stable diffusion, steps or inference steps refer to the number of steps the diffusion process takes to generate samples. And remember, samples is just the intermediate latent images. Each step involves iterative refining the generated sample by adding noise and then denoising it. This will of course depend on the KSampler, basically the algorithm that is being used during the sampling process. Now for CFG, it's known as the classifier-free guidance scale, and this scale will determine whether we are going to follow the prompt. This classifier-free guidance, the CFG, the higher the CFG, the more the model will follow the prompt or the input image. And the less the CFG, the more freedom or randomness that the model will get in order to generate the image. The sampler and the scheduler, these two are basically the algorithm used when going through this step and trying to get to the clear image here. Now, some of the algorithm are converging. So let me zoom out a little bit. So basically, if you start from this latent image, and no matter the number of steps, you will always reach a similar output. So something like this. So even at this stage, we'll get a hint of this one. And if we continue on going, if we have more steps here, we're just continuing down the same thing. We will keep having the same picture. Maybe if the steps count a little bit too high, we may get noise at the end, but the overall composition of the image will still be the same. Now, if few of the algorithm are diverging, that means that, let's say at this point here, we are at step 20, but if we go to step 40, we'll get a completely different image. So it basically start to diverge from the image. So here's an example of a KSampler which converge towards one image. And right now I'm using Euler. With step 1, I get this image, and you can see something here. If I keep on going, step 2, 3, at step 5, we can see a cat. That was my prompt, by the way, a cat. We have a table, and as I increase the number of steps, we are getting the same cat in the same position, just adding more detail to the overall image. So at step 15, again, is the same cat sitting in the same position. We have the same table, the element in the background, just adding some more detail. So if I increase the number of steps at 40, you can see it's again the same cat. Now I've changed the KSampler to Euler A. A stands for Ancestral, and basically what's going to happen is that at each step we are going to add a little bit of noise during the sampling steps. And this is an example of a KSampler that's going to diverge, and it just cannot converge towards a single image. The same thing, we have the cat here, and now you can see we have two cats at step 3. Step 4, the cat is changing into a woman. And right now what we are seeing is that the CFG is too low because of those added noise. And by the way, for the Euler one, I was using the same CFG and it was able to give me the cat all the way until step 40. But for Euler A, I've increased the CFG, and you can see the image is slightly burned now, but that's okay. We are at step number 1. We go at step number 3, we now have a cat. Step 4, we have a different cat. Step 5, different cat. And as I keep on going through the number of steps, you will see that the cat changes, the environment as well changes, and keeps on going like this. And this is something that you'll need to look into when you are downloading the model. Try to see which of the samplers are going to work best for that particular model. Now, positive and negative, this is just the conditioning, the text that we are passing over to it. Now, latent image, that's just coming from the empty latent or from an input image, which you can encode into a latent space. Okay, so for the noise scheduler, it's basically determining how much noise there should be at each step. And here's an example of one. So let's make it as if this is step number 1, and we have step number 20 here, and then we have 10 somewhere in the middle. So at step number 1, we have the highest amount of noise, and then as it goes, we decrease the number of noise through each step. And the noise scheduler is the one responsible to determine how much noise there should be at each step. And that is because the sampler will use this estimation to determine how much noise it should remove at each step. And lastly, we have denoise, and the denoising factor is used in image to image workflow. We basically have an image, an input image, which we pass to the VAE encode, get a latent space image from it, and we pass that over to the KSampler. Now, the denoising factor is telling us how much of that image do we want to keep and how much do we want to change. So if we have a denoising factor of 1.0, it means that we do not want to keep anything from the original image and we want to change everything. And if we have a denoising factor of 0.25 or 25%, it means that we want to change 25% of the image and keep 75% of it. So a low denoising factor means that we want to keep the image. A high denoising factor, we want to change that image. The more we want to change it. All right, so we've taken a look at how Stable Diffusion works, what are the different nodes for text to image, as well as image to image work. Let's talk about a couple of nodes which are built in ComfyUI. The first one is we go from add node, Utils, node, and this one is simple. You just add nodes to yourself. So what I usually do for this one is if I'm using SDXL models, they have very specific resolution that you want to use. There's something like, I believe like this, then 1024 by 1024. You can have these nodes to yourself here. It will stay in your workflow, and anytime you need to refer to it, you can just check it. Okay, these are the different resolution or maybe the different KSampler settings. You can add all of that into the nodes. We've already seen the primitive. Primitive is basically just going to give you an input widget, and it's going to also give you control. So for example, here we have the steps at 4. We also have CFG 1. Let's say we want to see what is the best CFG for this model. I can convert the CFG to input, take the CFG into my primitive node. Now I have control after each generation. So control after generation here. I can change this to incremental. And let's say I want to start with, let's say 0.1. I can click on the Q prompt, and you will see the moment I click on Q prompt, let me show my view Q. I have 1. It incremented it to 0.2. If I click on Q prompt again, it goes to 0.3 and it keeps on going. So I can click on Q prompt multiple times. I can also use the extra option and do a batch count. Then it will auto increment here, depending on how many I have. You can just wait for it to complete, look at the output images and see which one is the best and select that one. Since we have the node here, you can add a node, let's say best CFG, and then put your CFG again. And the last one that is under Utils is the Reroute. And this one is you have like big workflows. Let's say you're going from here to somewhere here, and let's bring another KSampler here. So I want this model to go all the way here to this KSampler, and you can see it's quite far. It's a little bit difficult for me to grab this, go over there. So I can use this reroute node by taking the model into the reroute And now I have like a point. I can drag this over to where I need it and connect it with it. That's basically the reroute node. Now on the samplers, you will see we have custom samplers, schedulers, samplers, and signals. Those are basically doing the same as the KSampler, just additional control, or if we have any experimental node that came out, it would usually use a custom sampler if it has not been implemented in the normal sampler. Now we also have the KSampler Advance, and this one gives you a little bit more control over how the noise will go from one KSampler to another. So for example, let's say I'm doing 2 pass. I'm going from this first KSampler to the second KSampler. I can choose to return with leftover noise. And then when I pass that over to the second one will continue with whatever noise was remaining. For that to work, I will need to change the end at steps. Let's say, for example, here we are doing 20 steps, and I can do the first 10 steps with this KSampler, and the remaining 10 with the remaining noise will go over to the second KSampler, and then it's going to continuous generation. You will see this often in SDXL base workflows. Basically, we have 2 different checkpoints there. We have the base SDXL, and then we have the refiner checkpoint. So the refiner we use the second KSampler, and then the base one will have the first KSampler. Now, of course, we have other nodes like Upscale, Latent. And if you understand this basic workflow, all the necessary component to generate text to image as well as image to image, the rest is pretty self-explanatory. So if you go into Latent, we have Upscale Latent, and it's just going to take Latent, not this one, from the KSampler, and then upscale it. So right now we are 1024. I'm going to do twice, so 2048. And you're just going to double it. So you'll need to go from this upscaler to another KSampler here in order to again go through this step here. All right, so this video is getting a little bit long. I think this is where I'm going to stop it. If you have a specific node or a specific group of nodes you want me to cover in a future video, let me know in the comments down below. If you've watched until the very end and you've learned something new, let me know by clicking on the like button. Subscribe to the channel if you have not done so, and I will see you in the next one.